Here we are. Cool. So I'll take over. Thanks a lot for your no. Okay, nevertheless, let's start. I think we have some technical problems on the side of Paul. I'm happy to introduce you to this Brainfood Talk about reactive systems and into the reactive systems. People who know me know that I'm usually talking quite a lot about reactive systems. So I try to shuffle this talk a little bit around, add some things, remove some things so that everybody can take something from this. So it's an intro with a little bit of an outlook on how we utilize reactive systems here at Square with our partners. First things first, my name is David Leitner. I'm a coding architect here at Square. So whenever you need something which is unclear from this talk, which we cannot kind of answer in the Q&A, feel free to reach out and basically just use my email address or my Twitter handle to do so. What is asynchronous programming? Asynchronous programming is programming with or designing upon asynchronous data streams. I can hear you, I think. There are still some technical issues, I think. Can you mute yourself, Paul? Okay, great. Now, let's talk about programming. Let's talk about asynchronity in general. It's programming or designing upon asynchronous data streams. And this is where I actually would like to start, where I would like to give you an intro, what we are talking about today. Because in a nutshell, all we're doing is that we need to understand what is a stream. And surprisingly often, if I ask people what if they can explain to me the concept of streaming and streams, it's often very unclear, but that's not unusual in our industry. Many terminology we are using each day is yeah, sometimes means different things for different people. And so is streaming, and people who start with streams usually see it like this, right? Everything is a stream when you start reactive programming or going with reactive or stream-based systems. And when I explain streams at university where I'm teaching from time to time, I always use this very simple model of explaining them. So I think this makes a lot of sense because then we kind of remove a little bit the magic from what a stream actually is. And it turns out that we can just structure it as a kind of different data structure or just another data structure. And we think of data structures in programming, and this seems to be now very sophisticated, but it's actually very simple to understand. So stick with me. We have two axes. We have the axis of space and we have the axis of time. And in the axis of space, we kind of have synchronous singular space and synchronous time. And this is usually where value lives. And values have getters and setters. And beside this, if we go from singular space to plural space, we have something which we tend to call collections. And those collections usually have iterators and generators. So there's nothing really special about these data structures. These are synchronous data structures we have in nearly all kind of programming language or in all kind of paradigm out there, which we use for writing software. What's more interesting is if we move from synchronous time to asynchronous time. In this direction, we move from values to promises. So we stay in singular space, but we move to asynchronous time. And the promise is nothing else than what it says. It promises to give us a value somewhere in the future. Unfortunately, we all know that this promise doesn't always hold true, but in general, promises have a deferred and a resolver. And now there's only one spot missing. And usually when I explain this at the university or at conferences, I always ask what's up there right now, right? I cannot do this here in this format, but in general, people are quite aware what's missing there, right? Because if we move to plural space and stay in asynchronous time, then this is where streams are happening. So streams are like collections combined with promises, so values coming over time. We do not know when it ends. We do not actually know when it starts, but we do not have them instantly. And they usually consist of a subscriber and a emitter. So streams are just another data structure. There is no magic behind streams. There's nothing which is kind of fluffy or new or which is rocket science there. It's just another data structure. The only difference is that most technologies we use these days don't treat them as first-class citizens. More and more technologies start to do this, like they did with promises a few years ago. We also see streams becoming native in most technologies and frameworks out there. Before this, this is where we introduced reactive extensions, for example, to kind of extend languages with this data structure of streams. So nothing else than, just giving these data structures to prominent programming language, like, for example, ArcJava or ArcGIS for Java or JavaScript, right? So now we understand what streams are. We need to further understand what do we mean by programming or designing upon asynchronous data streams, because this is where reactive systems start. And I usually always explain things on the very low level, on software design, on code level, and then try to kind of publish or push these concepts further into architecture, because surprisingly often this works. Surprisingly often we see concepts which we used in kind of software design, which we can very similarly explain, apply to software architecture. So let's figure out, first of all, reactive programming. Again, something which is kind of a very hard to understand term for people who never did this. And that's why I would like to give you a very, very simple example what reactive programming in a nutshell actually means. And again, an example I usually bring because I just like it a lot, and I think it brings home the point. So we have two variables, a counter which with a value of 2 and doubled, which is counter multiplied by 2. So in this case, 4. When we do assertion now, we say doubled is 4, right? This makes sense. This is true. The test will be successful. When we now change this code in a way that we update the counter to 3, and then basically, first of all, the comment is, of course, genius. But when we then would do an assertion, we could assume, doubled is counter multiplied by 2, so doubled should be 6. But we all know that that's not the case, right? And this is where the heart of us as a reactive community breaks. Because what we would need to do in classical imperative programming is that we would need to set the doubled, again, to be counter multiplied by 2. And if we do this, we can then make an assertion which says doubled is equal to 6, and this test will actually be successful. And that's the problem. That's the problem, as I mentioned before, in this concept of this way how we program these days in most situations. We have this relationship between counter and doubled very implicit. It's just an idea that exists in the minds of us as programmers, but it actually should be very explicit. It should be part of a language that exists over all time. Doesn't matter where or when we touch doubled or counter. So counter and double should actually be bound. And a guy who found this out quite a while ago is Paul Stovall on his blog. He writes about this destiny operator, this idea of a destiny operator. And this idea of a destiny operator would look like this. So we see here this equal sign changed a little bit, and it's just a concept. But when we would have a destiny operator in modern programming languages, we could say, counter is 3, and doubled would then actually successfully assert to be 6. And if we want to implement such a destiny operator, this usually always works with streams. So we usually have a counter, which is not just a single value anymore, but it's a stream with an initial value of 2 now. So if we consider this on the right-hand side, what's currently in our stream, it's 1 value, and this value is 2. To kind of derive double then from this, we would make something which we tend to call a stream transformation. We would take counter, map it, and multiply it by 2. So this would result in another stream, a stream of doubled, and this would have a value of 4. If we now kind of want to change doubled, we just need to understand our counter. We need to understand that we project the data from our counter stream into our doubled stream. That's a very important sentence, which we'll come back later on when we talk about reactive systems. And what we do is, when we update the counter, ultimately, we just emit a new value to this counter stream. So we emit the value of 3, and this would actually just add the value to the stream. And as we derive from the counter stream into a doubled stream, this would basically also update this stream and include a value of 6. And that's interesting now, because if we now say assert that the current value of doubled is 6, then this will actually work. And although this is still example code, this looks very similar in reality. So if we take a look, for example, at RxJS, which is an implementation of a stream data structure for JavaScript, then we would have something like this. We would have a behavior subject with the number of 2. So behavior subject is just a stream with an initial value. And when we want to have it doubled, we would just pipe this counter and would map it again and multiply its values by 2. And if we would then emit a variable 3 onto this and would make an assertion that the current value of doubled is 6, then this would work. And that's real code now, right? That's not artificial code anymore. That's real code. This code would work. You would be able to run this code in your JavaScript or TypeScript console. And more modern concepts, like, for example, Svelte, they even bring this destiny operator from Paul Stoffel even a step further. Because what you could do in Svelte, for example, you could say you just define a variable counter. Yeah, there's a value of 2. And then you basically define a variable of doubled, but you prefix it. You prefix it with this small little $sign here on front. And then you would just be able to multiply this counter by 2. And what Svelte in the background is doing, they're kind of setting up this whole streaming for you in the background. And whenever you change the counter now, you change it to 3, this will automatically update the doubled value to 6. Because with this $sign, we told Svelte, hey, this is a reactive value. This is something which needs to change if one of its dependencies is changing, and one of its dependencies in this situation is counter. So this code, again, would work. This is valid Svelte code. So this is already very, very close to the original idea of such a destiny operator. And more modern frameworks, especially in the front-end context, where reactivity is kind of a big thing, has ever been for a couple of years now. We see more and more ideas like this emerging. And if you're really interested in this, you should probably take a look at Solid.js, which I think has very beautiful concepts to enable us in a very simple way to do this kind of reactive programming. And as I mentioned before, we can apply those concepts of reactive programming also on reactive architectures and systems as well. And of course, hope that they make sense. But in reality, that's what I tried to explain in the beginning. We just need to understand this concept of reactivity. And then we can apply this concept on reactivity in the terms of reactive programming when we write code, but also in the terms of architecture when we talk about reactive systems. So let's look at how this concept of reactivity would look there. Well, let's just take a very simple example domain of beloved microservice architecture we usually have these days. So let's consider web banking. Everybody, I guess, these days uses web banking. So it's a domain which everybody should be familiar with it. And let's say we do a new payment on web banking. So 20 euros are transferred from my account to, for example, Lisa's account. And if I confirm this payment, then this makes a request to transfer some money from the user microservice, and the user microservice then calls the account microservice to trigger a payment, and this account microservice then actually calls the ledger to create a transaction. And yeah, the ledger then says, yeah, cool, I created the transaction. The account service said, hey, I triggered the payment successful, and the user microservice sends back to the web banking application that, hey, David, your payment was successful. And that's nice, but unfortunately, of course, that's the happy part, right? In most situations, it works a little bit different. In most situations, we would trigger a new payment. The user microservice goes to the account microservice. The account microservice tries to go to the ledger, but the ledger, is not in good mood right now. And this, of course, is not the best user experience, first of all, because if you ever triggered a payment that didn't get a response, it feels kind of bad, right? You get kind of a bad feeling in your overall body, because you say, oh shit, did it work? No, did it not work? Should I press refresh? Should I not press refresh? Not that simple, so not that cool. But even if the ledger would now come back, and would send back a response, that's something actually where we see problems, because, as I mentioned before, this kind of comes to this downside of what happens if one service is not available. How do we kind of ensure that our users can still use our services? And we try to solve these problems of these synchronously integrated microservices by, utilizing retries, and then we kind of need to configure those retries correctly, that we don't shoot ourselves into our own knee by making a DDoS attack on our services because we didn't kind of, align the retries between our services. We have this idea of timeouts. We have this idea of circuit breakers. We had all these ideas, and we kind of need to synchronize them then, as I mentioned before, between servers. And it's kind of complex. It didn't really work out. It never really worked out from our perspective, or from my perspective. And this was kind of the first generation we saw for microservices, synchronously integrated microservices. And of course, we've seen this as an industry. We observe this problem that synchronously integrating service to each service is usually not the best idea, and leads to this distributed monoliths. And what we then did, of course, is that we said, we isolate away those bottlenecks. So, for example, the ledger obviously is something which from time to time is not available. Then we kind of move this ledger away and put a queue in between, right? And if I now perform a payment, I trigger this payment, send it to the user service sends it to the account service, and the account service just puts it in the queue. And at this point in time, we can tell the user, your payment was accepted. And there's an important change in terms of wording, because the payment was now accepted. It was not created anymore. We told the user, hey, we got your payment. We will work on it somewhere in the future. And in this future, this ledger will probably available and will be able to kind of process this payment. And then the payment is, of course, through. But the user in this situation will then just later on, at some point in time, we will promise him that we will do the payment, but we just didn't do it right now. And this solves a lot of problem, but if you isolate one bottleneck in a system, that's just the nature of systems, that you kind of will spot the next bottleneck immediately. And maybe the account service then is the bottleneck, and we put queues between the user service and the account service, and then we start to put queues between the web banking and the user service. And these were the big times of RabbitMQ or ActiveMQ, these all AMQP solutions, which made a lot of sense and still make a lot of sense in many situations. And this is where we kind of moved from this fully synchronously integrated microservices into the second generation of microservices, which we tend to call message-driven asynchronously integrated microservices. And that's kind of interesting. But if you take a look at this overall picture, there's a much bigger problem in this overall idea or approach of how we build systems, right? There's a hidden elephant in the room, we could say. And the problem is, if you would talk to a product owner, or if you would have a product owner, he would probably give you some kind of requirements he expects your team to implement. And if you work for a bank, a requirement could actually just be the thing which we just did. We could say, as a customer, I want my transactions to be booked by the ledger. So someone in the ledger needs to do this, right? Well, that's not really a good user story, because as a customer, you probably don't care about the concept of transactions or where it is stored, if it's stored in a ledger or if it's stored somewhere else, right? A better customer user story would probably be if your product owner would tell you, as a customer, I want the account service to update my balance, right? So whenever a new transaction is triggered, I want to see this reflected in my balance, of course. Well, not really, still not, right? That's not something which really drives you to use this bank to see an updated balance when you do a transaction. That's not really the value of a user story. What a good product owner would probably tell you is that as a customer, I want to transfer money to someone else. That's what the user is doing here. He selects, I want to transfer money to Lisa. And we see here this yellow box already spawning, because this leads to this idea that if you come up with such a requirement, then you would need to go to the user service with, hey, we get this new request, we get this kind of feature that we can transfer money. So somebody calls you, please provide an API endpoint to transfer money, or kind of listen to a queue. And then user service team, please talk to the account service guys, because they kind of need to trigger a payment for you. So you need to call them. They must provide you an API, or they must define the event they're looking or listening to. And please, if the account team did this, they should please talk to the ledger team to do the transaction finally. And that's kind of how it's not working, right? Because then you need 3 teams to just implement a simple feature. And this resulted in this idea of the entity service anti-pattern. That's probably one of the most prominent anti-patterns we see in microservices these days, that people are building microservices the same way as they design database entities. And this is, I would say, kind of explainable because we design databases like this and we design our monoliths around entities, but doesn't really work in microservices anymore. That's why we understood that we should create services along customer journeys, and should not follow this based on how we store our entities in databases, or we structure them on persistence level. And the interesting part is, I just usually give my students some papers during university lectures, and one of them I always give them is this age-old paper from Panos from 1972, where he writes on the criteria to decompose systems into modules. And that's kind of super interesting, because he actually back then already understood there are these 2 ways of how we can structure or how we can slice modules in our systems, based on user journeys, I think he calls them use cases there, or based on data objects or entities. And he figures out at the end of the paper that it's probably in many situations much better to structure modules around use cases. And it just took us now nearly 50 years to re-understand this. And I think we kind of agreed on this as an industry, that we should not slice microservices based on entities. We should slice them based on user journeys. And there was a Brainfood talk a few months ago from Clemens and Christoph, where they actually tried to dig deeper into this idea how we should actually slice microservices. And well, we did this, right? We said, okay, let's introduce customer journeys. And what we did is what we often do in software engineering. We solve problems with introducing an additional layer. And in this case, we renamed our microservices to domain services and introduced the concept of journey services. And those journey services then call the user account and the ledger service to do a payment. And if you now go back to your product owner, he will hate you, right? Because instead of going to 3 teams, he must need to go to 4 teams now. And even worse, in many situations, we use the concept of backend for frontends to kind of build these journey services. And then you have a backend for frontend for web, and you have a backend for frontend for mobile. And your product owner now would probably need to go to 5 teams. And if you change something in the payment flow, you would basically need to change it on 2 places. Yeah, I just brought up this slide here because we see this very often in our daily work, that the concept of very good concept of backend for frontends from Sam Newman is unfortunately very often used in a faulty way. And so just a short disclaimer again that we should not put domain logic into our backend for frontends. Yeah, backend for frontends are about UI specific aggregation to get rid of overfetching and over requesting, but we shouldn't start to duplicate domain logic there. But more this in a specific talk, which you can find on the Square website. So when we do this now, when we introduce these journey services, beside the fact that it doesn't really make our product owner happy, we could do this, of course, and would say we can introduce another balance service, and we could introduce another kind of customer journey service. But obviously, we do this because we have data which all these customer journeys need, right? And in this situation, this could, for example, be our account data. Because if you do a payment, you need to have a user account. And if you need to check a balance, you obviously also need to check the account to get the balance for a given account. And this is what I usually call the customer journey and entity data mismatch problem. Yeah, I didn't figure out a better name for it. So if you have one, let me know. But what I mean with this usually is that we have this mismatch. We have this mismatch of customer journeys and entity data because every system kind of has these entities, right? These entities could be users, these entities could be accounts and transactions in our case. And every system has this kind of customer journeys, right? So you see, we trigger a new payment, or we onboard a new customer, or we do some fraud detection based on transactions. These are journeys through our system. And trigger a new payment would probably need user data, would probably need account data, and would probably need transaction data. Onboarding a user would probably need a user to onboard him and create him, and would probably also create an account for him. And fraud detection would probably need accounts and transactions. So we see this overlap here. All of our customer journeys in this very artificial example, of course, but you get the point, are using the entity of accounts. And this is the problem which we try to solve by this additional journey service layer, that we have these entity services in the background still, and we have these journey services in front of them. And of course, this leads to a lot of dependencies between the systems. And as we've just seen, if the account service is not available anymore, this will have a huge impact on our overall system, because our overall system will not probably work anymore because nobody really can access those accounts. So the problem is data. The problem is that we have these services which provide us this data of, for example, accounts, and then they are the single point of failure. So how could we solve this problem? Well, we could, for example, say each service gets its own set of data. So each service gets the data it actually needs, right? That's a nice idea, because this would fully isolate those services and we have full service autonomy. So if onboarding doesn't work, the payment customer journey is not affected, and the fraud detection customer journey is also not affected. But of course, that's just the concept again, which would lead to a lot of data duplication, because we cannot kind of have accounts in 3 different services. We can, but then we have complex data synchronization and all the things. And the first thing which you usually should do when you build a distributed systems, and I think that's what we still often lack in doing, is that you need to clarify who owns which data. And I don't mean that you need to kind of make big workshops to come up with a canonical data model for your overall organization. But what I mean is that when you kind of need to have an entity in your service, you always need to understand, am I the owner of this entity right now, or is it somebody else? And that's important, because if we do this, we could say, accounts are not owned by entity service, but accounts or users are owned by one of those customer journey services. And it's, of course, a kind of, talk on its own to figure out where should we move which data. But usually for me, simple questions I ask myself is who usually creates this entity initially and who updates it most. So for example, onboarding makes sense that they own the user because they actually create it. Payments make sense that they own the accounts and the transactions because they probably mostly modify them. And if the payment service then would need a user, then it would just call the onboarding service and ask for a user. But then we're back again. Then we're back in the first picture where we have the synchronous call. And if our onboarding service goes down, our payment service would probably not work anymore in a way as we expect him to work. And then we can, of course, use a cache, right? We know we can do this, but as I said in the beginning, this comes with all these downsides of cache invalidation. And really just we try to solve this problem by complexity. So there needs to be a better solution, obviously, for this. And now I'm coming back to this super simple code example from the beginning where I said you need to remember this sentence where I said we project data from our counter variable into our doubled variable. And that's interesting because we could think of a very similar concept. We could think we project the user from our onboarding service into our payment service. So we do not fetch the user anymore from our payment service from our onboarding service, but we do it the other way around. We say the onboarding service kind of projects data into the payment service. So whenever an onboarding service creates a user, we kind of want to have this one projected into our payment service. And in more domain-driven design terms, we would call this on the left-hand side a user aggregate, on the right-hand side a user read model. And when we change a user, we would have a user change command. And when the user was successfully changed, we would publish kind of a user changed event. And this user changed event would then on the other side again update the user read model. And basically that's CQS in a nutshell. Yeah, it's not much more. That's this kind of unidirectional flow of data changes and data read models. And this leads us again, as we've seen in reactive programming already, this leads us again back to the concept of streams. Because when we want to achieve this, we usually need a stream where we store this user changed event. And this user changed event then get transformed to kind of be applied against the user read model. And this is where we use all these great technologies like Kafka, Pulsar, CubeMQ if you want to stay very Kubernetes native, or you could probably still use a simple old Redis to achieve something like this. So I'm not going into technologies today, but there are many ways to achieve such architecture. One we see these days very often uses, of course, Apache Kafka, which kind of allows us to easily kind of spin up streams as shown on this example picture. So how would this law work in our use case? Well, as I said, whenever a user kind of gets onboarded or updated, this would trigger an event on our stream. And we would consume this event of a changed user and would kind of put it into the payment service. And what the payment service would then probably do is it would wait for all the events that are coming from the onboarding service and would put them into a projection. So projection is nothing else than a read model. So we project data from one service into another service. That's why we call the thing projection. Sometimes we call it read model. Again, not fully clarified or well-defined, but in general, we mean kind of a read model which stores the user in a way as we need it on the payment service. And if the user changes again, we consume it again and we would probably then again update our projection. And that's interesting because we can do this then for all of these data. We could do this for transactions which are consumed in the fraud detection use case and so on and so forth. And the cool thing is if now the onboarding service goes down, it doesn't really matter to our payment service because we have all the users we need in our projection. And this again makes our services very autonomous and makes them very resilient in terms of they not have a runtime dependency to each other. And we can think of it like a reverse cache because this cache never runs stale, more or less. We never need to do this cache invalidation because we never need to understand, should I go to the service and ask for this user again because probably it's old, because the onboarding service pushes us user changes. So whenever we get an event that the user changed, we just update our projection. So we turn this idea of caching a little bit around. But didn't we introduce eventual consistency there? That's usually the question people ask, and I fully understand this point. But eventual consistency is a very big topic. And again, different people mean different things by eventual consistency. And I would really love to go into detail about what I call the different phases of eventual consistency, but I think this would not fit into the time slot. So if you're interested in this, go to our website /slides. You'll find a talk about the rise of reactive microservices, where I go a little bit deeper into these different approaches and ideas or different phases of eventual consistency and how we can get rid of them. But the spoiler, the too long don't read, is that eventual consistency is often used as a knockout argument for such architectural styles, but isn't in most cases. Yeah, in most cases, we find ways to deal with eventual consistency or keep it that low that it doesn't really hurt us anymore. So we've seen this. We've seen this advantage that we can use our payment service now, even if our onboarding service would be down, because we projected all the users into our payment service. Well, let's make this a little bit more concrete. And for me, a kind of an inspiring project was one of the first microservice projects I've seen at a bank, where in the beginning there was kind of a very interesting research, which I often say is probably one of the most interesting research I've seen in this area, even if it's not super high sophisticated. But we were building a new kind of customer banking back then. And it was researched how often people actually use which features when they open their mobile banking application. And the results were quite interesting, because 93% of all the users just show balances and show latest transactions. And then 3% of users initiate new payment, and 4% of users do any other functionality. And that's interesting, because these numbers actually show you a lot. They first of all give you a good insight into architecture. We will talk about this in a second. But on the other side, they would also give you a good insight in how you need to prioritize your features, right? If you build a new mobile banking application, probably it's more important to have a really good user experience in showing latest transactions and balances, because instead of figuring out 3 or 4 months how you can finally implement this lock a card feature, because nobody would ever probably use it, at least not in that intense, as people would just take the phone, check what is my current balance and what are my 5 latest transactions, right? And if we know this information, then this has an impact on architectural decisions, because in a nutshell, that's a non-functional requirement. A non-functional requirement which says us, whatever happens, ensure that the user can see the latest balance or the latest transactions and the current balance. And if you want to achieve this, we can do this exactly by the concept which I told you before. So if a user triggers a transaction, this transaction would kind of be in the payment service and would from there on be published to a stream. And the overview service just consumes the stream, then takes it and puts it into its read model. And whenever somebody wants to read now from this overview customer journey to show the user the latest balance and the latest transaction, then he would just go to this overview service. And the important part is here, he would just go to the projection. He would never go to the payment service, because he has all the transactions in the way as he needs them into his overview first service. And if now the onboarding service fails, we don't care. We can show the user the current balance and the latest transactions. And even if our payment service fails, we don't care, because we can show the user our latest transaction and the current balance. And if our overall system fails, right, we probably care. But in the context of showing the user the latest transaction, the current balance, we don't care, because we can still do so. So 93% of our users would still kind of be able to use the functionality they need to use, and they can still perform this, right? And that's a good example that we need to understand the business. We need to understand the requirements to select the right architectures. And for this use case, it's probably a fit made in heaven. Another thing is what we can easily achieve with this reactive architectures that we can easily scale out our system. We can easily spin up a second overview service. If you see, there's so much interest in current balances, we just spin up a second instance, build up a new projection, consume all the transactions and build up this read model. And we can then just forward to one of those two services. And if one of those two services fails, the other one is still available. So we have easy possibilities to horizontally scale our system, which in general, of course, makes it more resilient again. And one more thing, which is often forgotten when we talk about reactive system, is the fact that if we trigger a new payment, if I perform a payment or Lisa performs a payment to me, then this would trigger a new transaction on the stream. We could consume this transaction, would put it in our read model, and actually we could even push this event down to our UI and say, hey, there's a new transaction. This would probably add a new transaction in our list and would immediately also update our balance. And this is where we, for example, often use GraphQL because it treats kind of subscriptions as first-class citizens. It's just like a query, just in a kind of a different type and shape, and helps us a lot to build this kind of end-to-end reactive systems with utilizing mutations and subscriptions of GraphQL. So out of the box, real-time capabilities is something we have. And another thing is, when we work with legacy systems, right? We all work with legacy systems these days. I have the feeling, because there are so many around there, then it's a tough job usually. And even if the legacy system is tough, usually the legacy database is even tougher. And these databases usually contain a lot of important data, and in many situations, important reference data. And one way to kind of tackle these legacy systems is to kind of stream out this data from those databases by utilizing something like change data capture. And for example, whenever in this legacy database a user is changed, we kind of consume these events and put them into our services, into our user read models of these given services. And this would allow us that even if our legacy system goes down, we could still utilize the power of our new services. So this is just one tool, of course, of many to work with legacy systems, but it's often in our tool belts when we come into situations where we need to strengthen legacy systems. So this is kind of the third generation of microservices built on reactive data streams, and they give us high resilience, they give us horizontal scaling, they give us real-time integration, they give us actually a good integration with legacy systems. But not really the end yet, if we talk about reactivity and streams. Because we need to understand these different dimensions of scaling which are out there. And we talked a little bit about horizontal scaling, and I guess everybody is aware of the difference between vertical scaling and horizontal scaling. Instead of putting more power into our machines and putting more memory into our machines, we these days usually go in this direction of saying, we have more instances of this service because it's usually more cost efficient and easier to achieve in cloud-native environments. And these services then, of course, kind of have their own read models, which they can consume from streams. That's something which is kind of complex. So in many situations, these services all consume the same read model, which they share, which then again is kind of a bottleneck. But again, in the talk I showed previously, we go a little bit more into detail on this. But one way to solve this problem, to really scale up the read model, because even if you would go into this direction, it's kind of cost inefficient that every service needs to consume all the events all the time. That's why I mentioned that we usually do it like this. A way to kind of overcome this problem in thinking of the dimension of sharding. And sharding is nothing else than taking those services and sharding them into groups. And for example, groups could be users who use those services, so alphabetically, or we do it based on countries. So users from Austria go to this service, users from Great Britain go to this instance of a service, and users from Hungary go to another instance of a service. And we could even combine these concepts. We could even horizontally scale sharded architecture. But the important part is that the projection is here very easy and cost efficient to generate, because we just need transactions from users from Austria on our first service instance, and we just need transactions from users from Great Britain for all the other services running in the second shard. And sharding is important if we think about scaling this kind of reactive stream-based architectures, because what you usually get is you would get this user triggered a payment event. And this would then go into a stream. And streams these days usually work with partitions, and partitions are nothing else than the concept of sharding, just with a different name. So if this payment was triggered by a British user, then it would probably go to partition 1 for whatever reason, because we say in partition 1 all the British users put their transaction into. And then we have payment services listening to this stream, and especially always listening to a single partition. And this payment service would then pick up this kind of message or this kind of event triggered by a British user, would forward it to another stream and would put it again in the first partition, and so on and so forth. So we would do the fraud detection. We would kind of say, okay, this is now a valid transaction, would put it into the ledger, and the ledger would ultimately say, okay, this transaction was successfully booked. And we have these fully independent shards within our system. And that allows us to easily scale this system, because, as I said before, the bottleneck in scaling are usually those read models. Because we could have now specific read models for this given shard. So each shard would have its own read model where it just needs to consume its own shard, because it knows all my users from Great Britain are always in my shard. And this is why you use, for example, technologies like Apache Flink or Apache Kafka these days, which make a lot of sense to help us in building especially these stream-based sharded architectures. And then we could, for example, just simply put these transactions into a data sink like Elasticsearch, which actually even uses shards, right? They even call it shards, not partitions. And from there on, we could even build dedicated instances or spin up dedicated instances of web banking for each country, and would then kind of make them consume their given shard. And this is, of course, an architecture which allows us to kind of nearly independently scale. It just depends on the amount of shards we want to spin up, and we can push nearly unlimited infinite number of transactions through the system. So we can nearly scale them unlimited, and that's kind of the fourth generation of architectures in reactive systems. We see sharded and fully stream based. So they give us massive throughputs, they give us extreme scalability. So many choices. So let's quickly sum up, because that's usually what people are asking. Then they say, okay, what is now the right way for us? Is it not just enough if we do a kind of microservices with RabbitMQ in between? Or do we need a Kafka? Do we need to go for streaming? Where should we start? What solves our problem best? And I'm deeply sure about that. Our problem in many situations can be best solved by just spinning up an initial monolith, right? And of course, we all know that these monoliths at some point in time get to the end of their scalability in terms of team organization, but also in terms of technical scale. But I would stick with it as long as I somehow could. And then anyway, as I said, based on the teams or based on problems you see, you need to kind of split this up. And then in many situations, we would probably synchronously split up our monolith into two services talking to each other with the REST API. That's painful. This doesn't bring a lot of benefits, because these services are not independent. These services are not autonomous. They don't bring a lot of benefits in terms of resilience. They don't bring a lot of benefits in terms of having the team autonomous and being able to spin up their own and build up their own stuff. So that's something I usually would avoid. I would rather rethink, do I really need a distributed system at this point in time, or should I not just start to modularize a monolith? This is something which we call to monolith these days. And if we have a monolith, and if we still say, works fine, but we need this independent deployments now. We need teams to independently deploy to production, to independently give features to customers without waiting on kind of release trains for our monolith. Then I would directly go into this idea of asynchronously integrated microservices or systems. I would not go into this idea of synchronously integrated. I would directly start that we kind of need to asynchronously integrate those services, because this gives us then the benefit. This gives us the benefit these systems can work resilient independently from each other. And at some point in time, if you build these asynchronously integrated systems, you will get into this idea of sharing data between those. And then at some point in time, you will anyway figure out that it's sometimes much more efficient and easier to just shift the way around, to kind of shift the idea of not pulling data, but getting data pushed. And this is actually where you land in the idea of reactive systems. And if this is still not enough for you because you have massive scale requirements, then you can think probably of even sharding those reactive systems further to get massive throughput. So we have these architectures, we have all of them, and they all have the downsides and benefits. But as often in software architecture, we get features from software architectures, and the more we go to the right hand side on this image, the more features we get. But this also introduces a lot of complexity the more we go to the right side. So as always in software engineering, we buy features by complexity. And this, for us as engineers or as architects, it's most important to understand where is the perfect trade-off. How much features do we need and how much complexity do we pay for these features? And this is still a fit, right? And that's basically it, yeah. I cannot tell you what to do. I actually even didn't want to tell you what to do. I wanted to give you an intro to reactive systems, and I hope this was useful. And I even wanted to share you a little bit my insights or my opinions in how the future of fully stream-based architectures looks like. Thanks a lot. I hope this was useful, and I hope we still have some time for a short Q&A of questions you probably raised in the meantime. So I think this is usually the time when Paul should take over, but it's not so important. I can also answer them. Pavel asked, how do we deal with huge entities? That's a very good question. How do we deal with huge entities? I think there we need to differentiate how do we publish changes from those huge entities. We can usually do this by doing kind of pushing the current state of entity in so-called documents, or just pushing changes of entities with so-called events. Yeah, an event again is a term which means different things to different people. But these are the two things where we say we just push the delta, or we just always push the whole entity. And if you have huge entities, then these are usually aggregate roots, right? So you can kind of split them up into smaller aggregates, or you can split them up into smaller nodes in your aggregate. And one of them is the aggregate root, which I would always publish as a document, and the others I would just publish then probably as events. Yeah? But yeah, very complex question, and try to simplify the answer. But in general, of course, a problem if you have huge entities, then I would always think more in terms of aggregate roots. And if you have these aggregates, you kind of need to split them up probably into smaller partial entities, which then would produce their own events. Another question was, is the data stream now the single point of failure? Yeah, it definitely is. I think this is something which we need to be aware of, that if you build such a system, let's assume around pools or around Apache Kafka, then it's definitely your central point of failure. But the advantage that these systems are built in a way that you can scale them nearly independently, that they should not fail, right? You can run a Kafka on 32 nodes. Of course, costs some money, but you can do this, and then probably a good portion of these nodes can fail, and your Kafka would still be available. Yeah? But in general, yes, yeah, it's probably a central point of failure, especially if you do event sourcing. via them. So especially if you kind of event source those systems, because then your whole truth lies in those event streams. You could also do it another way, that you say this kind of stream just acts as an integration platform or integration channel, and you still have your data stored in relational databases from those services. Good. Another question, I think I can take another one, is does stream already mean asynchronously? Yeah, that's a good question. Again, I remember a few months ago, a student asked me a very similar question. What is asynchronously actually? Must it be a stream? To maybe answer it from another direction, no, it must not be a stream, right? You can also build an asynchronous REST API. That's what I often bring as an example. You can, instead of returning a created from a post request, return an accepted. And then you would kind of use a synchronous protocol like REST to build an asynchronous API, right? And in more general, we could even say kind of each integration is kind of asynchronously, because there's always some latency in between. So asynchronously is, again, I need to repeat myself, as a very vague defined term. Yeah, I think we in our industry often use terms to then kind of describe these concepts of reactivity. And that's probably sometimes problematic, but no, there must not be an stream in between to build a asynchronous system. But if you have a stream in between, it's probably a asynchronous system. But of course, there is this kind of callback pattern in RabbitMQ, which we all know, where you kind of build a synchronous request on an asynchronous message queue. Yeah, so hard to answer, but in general, I would say if you use streams, then you build a asynchronous system. Okay, I think we're out of time. It was really a pleasure to talk to you. I hope it was useful for most of you. I still see that we have a couple of visitors in our stream. Just a few announcements which I've left to give to you. First of all, of course, there's another Brainfood Talk very soon. So we do this once a month. It's about estimates. So it's about more on organizational terms, how we kind of enable teams to build software fast and good. And we will dive a little bit, or especially my colleagues will dive into business agility, and if estimates are actually a thing we should still do. And beside this, I think most of you probably have already seen it on social media. We are very happy to host the Socrates Day this year in Vienna. So we provide our office to do this wonderful conference. It's an conference. It stays for software craftsmanship and testing. So it's a conference just about how to build software to sharpen our skills and being good engineers. And it's about community, and it's about your ideas and your topics. So if you have time on October the 15th, it will take place in the bottom. You also see the link to the meetup. The amount of seats, I think, is very limited because it's an conference and we need some space. So we limited, I think, to 40 people. So be fast to reserve your spot there. That's all I have to share right now. Thanks a lot. It was wonderful. And I think we can end the stream here now.